Section 8.3, Stoichiometry of gaseous substances, mixtures, and reactions. So the ideal gas law, it can be modified to include density and molar mass. So we're going to start with the ideal gas law, and we're going to divide both sides by RT and V. And so what we end up with is N over V. So the sides have kind of crisscrossed here, to be clear. We end up with N over V equals P over RT. Next, we're going to multiply both sides by molar mass, which is going to be represented by the italic capital M here. Next thing I want you to recognize is this right here. On the left side, we have molar mass times N number of moles. And so molar mass times moles is just mass. So the italic M and the N here give us mass. So we get mass over volume equals P times M over RT. And what is mass over volume? It is density. It's important to note here, this density needs to be in grams per liters. So we can modify this equation to give us density equals pressure times molar mass divided by R times T. So let's look at an example of how we would use this type of equation. A gas was found to have a density of 0.0847 grams per liter at 17 degrees Celsius and a pressure of 760 torr. What is its molar mass and what is the gas? Okay, so we've got the density. It's already in grams per liter, so we're good there. But the pressure, we need to convert that to atmospheres. Our pressure still needs to be in atmospheres. So 760 torr is exactly 1 atmosphere. The temperature, we need to convert that to Kelvin. So that would be 290.15 Kelvin. And R is our ideal gas constant, which again is still 0.08206 liter atmosphere over mole Kelvin. Now we can plug this in. So D equals P times M over RT. So I'm going to rearrange this equation to solve for M. So multiply both sides by RT. So I get D times R times T, and then divide it by pressure. So the molar mass is equal to the density times the ideal gas constant times the temperature divided by the pressure. So now we can plug our values in. 0.0847 grams per liter, 0.08206 liter atmosphere mole Kelvin, 290.15 Kelvin, and 1 atmosphere. So units of atmospheres cancel, units of Kelvin cancel, and units of liters cancel. So the only units left are grams over moles. So when you solve for this, you get 2.02 grams per mole. So that solves the first part of the problem. What is its molar mass? Then second question, what is the gas? Well, the only gas with a molar mass that small would be hydrogen gas. It has a molar mass of approximately 2.02 grams per mole. Okay, so let's go ahead and have you try a problem. What is the density of oxygen gas at 37 degrees Celsius and 2.3 atmospheres? Alright, and the correct answer here is A, 2.9 grams per liter. Alright, next I'm going to talk about Dalton's law. So Dalton's law talks about the pressure of a mixture of gases. So Dalton's law of partial pressure, it's pretty easy. It's pretty straightforward. It's the total pressure of a mixture of ideal gases is equal to the sum of the partial pressures of the component gases. So if we imagine a scenario where we've got 3 cylinders filled with gases, these cylinders have the exact same volume. In one of them, the gas has a pressure of 300 kilopascals, one is 600 kilopascals, and one is 450 kilopascals. If we took these 3 gases and put them in the same cylinder, the new total pressure would be 1350 kilopascals. So you just sum the partial pressures of the gases. So really, the total pressure of a mixture of ideal gases is equal to the sum of the partial pressures of the component gases, or PT equals PA plus PB plus PC, and so on, however many gases you are combining together. So let's look at a quick example. This problem states that a 10-liter vessel contains 2.50 times 10 to the negative third moles of hydrogen gas, 1.00 times 10 to the negative third moles of helium, and 3.00 times 10 to the negative fourth moles of neon. They are all at 35 degrees Celsius. First, what are the partial pressures of each of the gases? And second, what is the total pressure of the container in atmospheres? So first, to answer A, what are the partial pressures of each of the gases? Well, you should notice that we've got the amount in moles, we've got the volume in liters, and we've got the temperature in Celsius, which we can convert to Kelvin. So to answer A, we need to use the ideal gas law. So pH2 is equal to N times R times T over V. which is 2.50 times 10 to the negative third, times R, 0.08206, times the temperature in Kelvin, 308.15 Kelvin, divided by the volume in liters. And so we get this for our partial pressure of hydrogen. And now we just repeat this for helium and for neon. You'll notice here the equations are the exact same. Same R value, obviously, same temperature and same volume. You're just changing the number of moles. 2.50 times 10 to the negative third for hydrogen, 1.00 times 10 to the negative third for helium, and 3.00 times 10 to the negative fourth for neon. So we get this partial pressure for hydrogen, this partial pressure for helium, and this partial pressure for neon. So this answers part A. To answer B, what is the total pressure in atmospheres? You simply sum these three pressures together, and you get 0.00961 atmospheres. Okay, next I want to talk about, well, what if you are given the total pressure and you want to find the partial pressure? To do this, you need to use mole fraction. So mole fraction is usually represented with this sort of capital italic X. Now, mole fraction is technically a unit of concentration. It's the number of moles of a component of a solution divided by the total number of moles. So it's just like mass percent or volume percent, percent composition. It's just the component that you're interested in divided by the total. So in this situation, number of moles of the component of this solution divided by the total number of moles. So if I want to find the partial pressure of a gas and I'm given the total pressure and I know the moles, all I need to do then is take the mole fraction of that component and multiply by the total pressure, and I can find the partial pressure of that component. So let's look at an example of how we use that. A gas mixture used for anesthesia contains 2.83 moles of oxygen, O2, and 8.41 moles of nitrous oxide, N2O. The total pressure of the mixture is 192 kilopascals. Part A asks what are the mole fractions of O2 and N2O, and then part B asks what are the partial pressures of O2 and N2O. So let's start by finding the mole fraction of O2. So this would be the number of moles of O2 divided by the total number of moles. So that would be 2.83 moles over 2.83 plus 8.41. This gives a mole fraction of 0.252. So then to find the pressure of oxygen gas, so I'm kind of jumping ahead to B here. To find the partial pressure of oxygen gas, I would take the mole fraction of oxygen gas and multiply by the total pressure of the mixture. So 0.252 times 192 kilopascals. This gives 48.4 kilopascals. Now I'm just going to repeat that process for nitrous oxide. So I'm going to take the number of moles of nitrous oxide divided by the total number of moles, which gives me a mole fraction of 0.748. And then finally, to find the partial pressure of nitrous oxide, I'll take the mole fraction of nitrous oxide, multiply by the total pressure of the mixture, and this gives 143.6 kilopascals. And these are my answers. Okay, quick knowledge check question. A mixture of three gases has a total pressure of 1380 millimeters mercury at 298 Kelvin. The mixture is analyzed and is found to contain 1.27 moles of CO2, 3.04 moles of CO, and 1.50 moles of argon. What is the partial pressure of argon? Okay, the correct answer here is B, 356 millimeters of mercury. So step one, you're going to want to find the mole fraction of argon, so that would be 1.50 moles argon, divided by the sum of these three, the total number of moles. Once you find that mole fraction, take that mole fraction and multiply it by the total pressure. Multiply by 1380 millimeters mercury, and you should get B, 356 millimeters mercury. Okay, briefly, I'm going to talk about collection of gases over water, but I'm going to talk about this in a little more detail when we get to our final lab of the semester, determination of molar mass. So when we go to do this experiment in class, we're going to be our setup is going to be pretty similar to this. So we are going to have a reaction in an Erlenmeyer flask here. This reaction produces gas, and we are going to have a stopper on that flask. And so the gas can escape through this little glass tubing here. It goes underwater and up into this collection flask. And so we're collecting over water. So the gas will bubble up through the water and it will collect up here. So the reason we're doing this is because we're going to equalize the pressure. So that we have kind of it's kind of like what we were talking about with manometers back in section 1. So the atmospheric pressure pushes down on the water, which helps to push the water up into the collection flask. But the gas that we're collecting here in this flask, it pushes down on the water. So we have these two opposing forces, the atmospheric pressure and the pressure of the gas that we're collecting. So the reason this is helpful is we are able to determine the pressure of the gas we collect inside here. We're going to say that this pressure is equal to the atmospheric pressure in the lab. The other thing I want to mention here is that while the vast majority of the gas that is in this collection flask is the gas that we're collecting, we're going to be collecting hydrogen gas in our lab, there is a little bit of water vapor. So the reason for that is liquid water at all temperatures, it is always evaporating. Now it evaporates more the closer to the boiling point you get, but even at room temperature, some water evaporates. So there will be a little bit of water vapor up here. So we're going to have to subtract that water vapor from the total pressure to find the pressure of the gas we're collecting. In our experiment, that'll be hydrogen gas. Now you'll look up this vapor pressure in a temperature in the back of our lab manual to be able to complete this in our lab. So briefly, if I showed you an example of how this is done, this problem states if 0.200 liters of argon is collected over water at a temperature of 26 degrees Celsius and a total pressure of 750 torr, what is the partial pressure of argon? So here, the total pressure, which again is equal to the atmospheric pressure, 750 torr, this is equal to the pressure of argon plus the pressure of that water vapor. So to find the partial pressure of just the argon, you would take the total pressure, 750 torr, and subtract the partial pressure of the water vapor, which you can find by looking up in a table. So there'll be an appendix at the back of our lab manual. So you use the temperature to find the vapor pressure of the water, which is 25.2 torr. So to find the partial pressure of the argon, it would be the total pressure, 750 torr minus the pressure of argon, 25.2 torr. This gives 725 torr. This would be your answer. Okay. Now, I mentioned earlier I'm going to go back to Avogadro's law, so I want to touch on that here. So Avogadro's law revisited. So remember that Avogadro's law relates volume and it relates the number of molecules, or it relates volume and moles. So earlier when we were looking at chemical equations, we would say that 1 molecule of N2 or 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3. Now, if everything in the equation is a gas, or just specifically the things we are relating are gases, with using Avogadro's law, we can kind of phrase it this way. We can kind of say that 1 volume of nitrogen combines with 3 volumes of hydrogen to make 2 volumes of ammonia. And this sounds kind of weird, but it makes sense conceptually since Avogadro's law just is a direct relationship between volume and moles. So we can use this to our advantage. So let's look at an example of how we would use this through a stoichiometry problem and kind of take a shortcut. So this problem states that propane, C3H8, is used in gas grills to provide the heat for cooking. What volume of O2, measured at 25 degrees Celsius and 760 torr, is required to react with 2.7 liters of propane measured under the same conditions of temperature and pressure? Assume the propane undergoes complete combustion. Okay, so there are 2 key things here. First, it says under the same conditions of temperature and pressure, so that's very important. The other thing that's very important here is that both of the reactants that we're relating to one another, they are both gases. Now, you could do this problem. There is a longer way you could do this problem, right? You could take the temperature, you could take the pressure, and you could take the volume, and you could solve for moles propane. Once you've solved for moles propane, you could then use stoichiometry to find moles oxygen gas. Once you've found moles oxygen gas, you could then again use the ideal gas law using moles, temperature, pressure, and to find the volume of oxygen gas, and that would give you your answer. You could certainly do this. This would just require 3 steps. However, because we are under the same conditions of temperature and pressure, and because these are both gases, we can take a shortcut here, and we can use Avogadro's law to relate the two. So we've got 2.7 liters of propane, so we can go ahead and use these coefficients from the balanced chemical equation as a conversion factor. And we can then say, well, 5 liters of O2 is equivalent to 1 liter of propane. So now liters of propane cancels, and we get the final answer, 13.5 liters, or when rounded to 2 sig figs, this would be 14 liters. And that's it. You're done. That's your final answer. So this is a really, really helpful shortcut you can use to save yourself some time. But I, again, want to emphasize both gases have to be, they both have to be gases, and they have to be under the same conditions of temperature and pressure. All right, let's look at a slightly more complicated example. This is a situation where we can't take that shortcut. This problem states what volume of hydrogen, H2, at 27 degrees Celsius and 723 torr may be prepared by the reaction of 8.88 8.88 grams of gallium with an excess of hydrochloric acid. So this is essentially a stoichiometry problem. We can't take a shortcut here because gallium is a solid, hydrogen is a gas here. We can't take that Avogadro's law shortcut. So we've got 8.88 grams of gallium. So what we need to do here is we need to do some stoichiometry. We need to convert from grams gallium to moles gallium, then from moles gallium to moles hydrogen gas, and then finally we will use the ideal gas law using moles, temperature, pressure, and the ideal gas constant to solve for volume hydrogen gas. So I'm going to convert from grams gallium to moles using the molar mass of gallium. Then I'm going to convert from moles gallium to moles hydrogen gas using the coefficients from the balanced chemical equation. And so I get 0.191 moles H2. Okay, now I've got moles hydrogen gas, and I can use my ideal gas constant. So I plug in moles, plug in the ideal gas constant, plug in that temperature in Kelvin, and I plug in that pressure in atmospheres. And so I get 4.95 liters, and this is my final answer. So make sure you understand the steps to this problem. You'll certainly, there's a high probability of you seeing something like this on the exam. Make sure you understand how to do a more complicated stoichiometry problem here with gases. Okay, so quick knowledge check question. What volume of carbon dioxide measured at 745 torr and 25 degrees Celsius can be produced by the fermentation of 10 grams of glucose? Glucose is C6H12O6. Its molar mass is given here. So you need to solve for volume CO2. All right, and the correct answer here is C, 2.77 liters. So you would convert from grams glucose to moles glucose, then from moles glucose to moles CO2, and finally you would use moles CO2, the ideal gas constant, 745 torr converted to atmospheres, 25 degrees Celsius converted to Kelvin, plug all that into the ideal gas law and solve for V, and you should get 2.77 liters. Okay, here are 4 practice problems for you to try. So pause the video, give these practice problems an attempt, and once you have done so, the answers are on the next slide. So here are the answers. And that concludes this section. I'll see you in the next video where we will talk about the final 2 sections together, 8.4 and 8.5.